So first I'd like to thank the organizers for this wonderful workshop. There's been some hitches along the way, but it's very nice. So today I'm going to talk about my joint work with Robert on denotational semantics for stabiliser quantum programs. And the paper is on the archive, and I've implemented the denotational semantics. But first, Robert's not here today, but I want to give him a shout out. He's a postdoc in Oxford, really chill guy. People can attest to this. And for me, I'm a postdoc in Paris-Saclay, and also I'm looking for a job if someone can hire me. So why do we need a stabiliser quantum programming language, and why do we need denotational semantics for this language? So my argument is that if we actually want to implement quantum algorithms, we need quantum error correction, because quantum computers are they're very noisy and they're not very fault tolerant, so you need to use these techniques. And of these techniques, the most prominent is stabiliser quantum error correction. And stabiliser quantum error correction doesn't just use unitary maps. There's a bunch of different operations which are needed. So we need Clifford unitaries and stabiliser states. We need Pauli measurements, classical operations, and classically controlled Pauli corrections. So these are like the general basic building blocks of a stabiliser error correction protocol. So this motivates the talk. We want a programming language which is like native to the stabiliser formalism, and we also want a denotational semantics which exactly captures this, so that we can reason about, optimize, and verify such quantum error correction protocols. So here's like a kind of vague, rough diagram of what you might want to do for a stabiliser quantum error correction protocol. So you have some, unitary or isometry which encodes things, and then you perform a Pauli measurement, and you apply some classical operations, and maybe some error occurs, and you want to apply some corrections to fix the error. So this is our language, and we have all of these operations. So you can compose things, you can initialize a classical bit, you can apply some classical transformation, you can discard the classical bit, and also there's some quantum operations. You can initialize a qubit, you can apply a unitary, and then there's some you can measure something and apply classical control. So you can mix the quantum and classical. So before I get to the denotational semantics, I want to do a bit of exposition. So in quantum theory, there's kind of three stages which I'll build things in. You have pure quantum theory, and you can add mixed states to get to mixed quantum theory, and you can go even further by adding classical types. So mathematically, pure quantum theory is just like linear algebra over the complex numbers, and you can apply this abstract construction to obtain completely positive maps between finite dimensional matrix algebras. And there's another abstract construction you can apply which gives you the same thing, but in terms of C-star algebras rather than matrix algebras. So I interpret the C-star algebras as your classical types if they're commutative. And for my purposes, I'm not going to care about mixed stuff, because it will just it's not useful for the exposition. So I'm going to go directly from pure state to mixed quantum computing with classical types. So this talk is all about stabiliser quantum programming. So I'm going to restrict my attention not to all pure state and mixed state quantum mechanics, but only those which are constructed using these operations I described. So you can apply the same abstract construction to pure stabiliser theory to obtain some stabiliser theory with classical types. And the denotational semantics which we're going to build starts with the observation that pure stabiliser circuits are equivalent to this category of relations over the finite field of characteristic P. And note that here on the left, the tensor product is given by the direct sum, whereas on the right is given by the bilinear tensor product. And the idea is by applying these same constructions, from which we go from pure stabiliser theory to stabiliser theory with classical types, we can do the same thing on the left and obtain an equivalent category. So I'm going to try to explain the semantics using examples. So in quantum stabilizer quantum error correction, we interpret errors as Pauli matrices. So I'm using this kind of ZX notation. So for any numbers x and z mod p, we can build the Pauli operator like this. And I'm going to denote it like the Pauli x is red and the Pauli z is green. So we don't have to think of things in terms of linear maps, but we can just think of a Pauli as a vector. So there's it's even dimensional, and the x is on the left and the z is on the right. So you can define this notion of stabilizer states. And a pure stabilizer state is determined by which Pauli operators you can apply to the state which act trivially. So it's the things which are kind of invariant under these errors. And it doesn't matter which way you go, from this point of view, we can see stabilizer states as subspaces. So you take all of the Pauli matrices which do nothing together. It's not an element anymore, it's a subspace. And more precisely, it's what's called an affine Lagrangian subspace. So it's a subspace with really nice structure. And here's an example. Ket 0 is such a subspace where the x stabilizers are fixed to be 0 and the z stabilizers can be anything. And similarly for the plus state, you just do the opposite thing. So the z stabilizers are fixed to be 0 and the x stabilizers can be anything. But like I said before, we don't want to just have stabilizer states. We also need more complicated operations. So if you just have some pure stabilizer circuit, then you can determine it in the same kind of way as for states in terms of how the Paulis flow through the operator. So if you take the Paulis on the right and you take the inverse, then now you have pairs of Pauli operators which act trivially on the operation. So we can think of such a stabilizer, pure stabilizer operation as a subspace, where the input dimension is on the left here and the output dimension is on the right. And in fact, we can think of this not just as a normal subspace, but as a relation, because there's some direction to what's in the input and what's in the output. And again, more precisely, this is an affine Lagrangian relation. So here's an example, the discrete Fourier transform. It takes your stabilizers here, swaps them, and then negates the Z stabilizer. And what's really nice about this representation of pure stabilizer quantum circuits is that you can compose them using a relational composition. So you have these two stabilizer circuits which you represent by relations, and you compose them by taking an element in the middle and taking the conjunction. And if you work with relations, then the composition is tractable, whereas if you just multiply the matrices naively, then it's exponential. So I talked about the pure stabilizer circuits, so now I'm going to move on to more complicated things like I described in the first slide. So how do we know if an error has occurred? We can't just use pure states. We have to go a bit further, and we have to perform measurement. So here we have our Z stabilizers and X stabilizers, and we're going to measure it in the Pauli Z basis. And what happens when you do this is you just forget the Z Pauli matrix, the Z Paulis, and you get the X Pauli out. So we can think of this as a relation as well. And what it does is it takes the two stabilizers, the X and the Zs, and it just forgets the Zs. And we're going to annotate the quantum subspace with a Q, because here this is a classical wire, and here this is a quantum wire. So they're really two different kinds of objects. So now that we have pure state stabilizer computation and we have measurement, how do we actually correct against the errors? Well, we have to perform a classically controlled Pauli operation. So here is the Pauli X gate. And as we all know, if you apply ket 0 to the Pauli X gate, it does nothing. If you apply ket 1, it's an X gate. And more generally, if you apply ket n, then it's x to the power of n gate. So in terms of relations, it looks like this. You have here on the top, you have your classical dit, and then you have your x and z stabilizers. And what this does is it takes the classical dit and just adds this to the x stabilizers, and you have this relation. So classical, quantum, quantum. So let's revisit this language that I described earlier. So all of the operations in this language were described on the previous slides. We have all of the classical things, the quantum things, and their interaction. But the question is, what is the denotational semantics of this language precisely? Like, what exactly do we generate? We have to ask one more thing, that the operations are physically realizable, which means that they have to be trace preserving. And in the relational picture, the trace corresponds to the relation, which just takes all of the x and z stabilizers and just kind of throws them away. So this gives us the denotational semantics. So the operational semantics are the trace preserving mixed stabilizer operations with classical types. The denotational semantics is the total affine relations with this symplectic modality I described. And then the syntax is this stabilizer programming language. And all of these three things are equivalent. It's not like an embedding in one or the other. It's all exactly the same. So here's a big table with all of the denotational semantics. You have your composition, dit initialization, qdit initialization, your classical operations, measurement, nothing operation, quantum discard, controlled, classically controlled x and z operations, and any Clifford unitary. With all of the types annotated. So there's some caveats which I swept under the rug. First, perhaps most annoyingly, is that all of this stuff only works for odd dimensions, and everyone cares about qubits, which is kind of a pain. But at least we can talk about qubits if we don't have access to the phase shift gates, like the S gate or the Hadamard gate. So it's not everything, but at least it's something. And also, in our denotational semantics, we only have a linear control. We can't like perform an AND gate on our bits. And we conjecture that if you add the AND gate, then the denotational semantics will detect the possible errors, but we'll forget about the probabilities. And when you're performing error correction, you don't care what probability an error has occurred with, but rather that an error has occurred or not. So that would be nice if we can prove it. And also, the language we gave is very low level. It's like an assembly language. So this is just more of a proof of concept. What would be really nice is if we can exploit this very nice, well-structured denotational semantics to build a more expressive syntax. You know, maybe have a type system which can tell us something about the properties of the stabilizer protocol. So can we verify or talk about fault tolerance within a more sophisticated type system? And yeah, basically the denotational semantics is exactly what people call the stabilizer formalism. And this is like, when people are reasoning about stabilizer or quantum error correction codes, they're not usually thinking of the complex matrices themselves, but rather the tableaus and these subspaces and so on. So this is kind of like the native semantics for doing this specific kind of computation. And I'd like to thank my talk. Thank you for attending my talk. And in honor of Robert, this is his official photo on his website. I've just chosen a random bar. So because we're running a bit late, maybe still, I suggest ask me questions here at the Delirium Cafe.
The other way is at the bottom.
Here.
We are at the top.
Okay.